This video will cover the second page of notes for the topic of graphing polynomials. Let's do example 2, where we need to graph p of x is equal to 7x cubed plus x. Again, we will go through the 6 steps we mentioned in the previous lecture video. Step 1 is to find the y-intercept by letting x is equal to 0 and solving for y. We find that the y-intercept is the point 0, 0. For step 2, we need to find the zeros, so we will factor p of x completely. Notice that we are not able to factor 7x squared plus 1. To find zeros, we will set x is equal to 0 and 7x squared plus 1 equal to 0. We find the zeros to be 0 and 2 imaginary values. So we only have the x-intercept of 0, 0, which is the same as the y-intercept, since we cannot graph imaginary values on our real graph. For step 3, since we did not use synthetic division, we do not have other points for our graph, so we'll skip this part. Step 4 is to talk about end behaviors. P of x is a cubic function with a positive leading coefficient, so the end behaviors will be similar to that of the parent cubic function. The left end of the graph will go down to negative infinity, while the right end of the graph will go up to positive infinity. For step 5, our zeros have a multiplicity of 1, and we will talk more about multiplicity in a moment. For step 6 and our graph, all we have is 1 point and the end behaviors. But we also have those 2 imaginary zeros. We will represent them with the wiggle in the graph as noted in the sketch. So let's talk about multiplicity. First start with this graph that we have right here, and we're going to see that if we're coming up from the far left of my graph, we go up, we're going to go through this x-intercept that we have right here of x is equal to negative 2, which creates the factor of x plus 2. So what we do know is that if you go through an x-intercept, either with a positive or a negative slope, you will have the multiplicity of 1. And that means that your factor will have an exponent of 1. As we continue with our graph, it will go up some value, come back down towards the x-intercept, and notice it will get to the x-intercept of negative 1. It kind of touches the x-axis and then bounces back up. If you have something like that, so here's your x-intercept, you approach it, touch it, and then bounce back, or touch it, approach it, and then bounce back, we say you have a multiplicity of 2. So we can see that the factor of x plus 1 has a multiplicity of 2, means it has an exponent of 2. It creates that negative 1 x-intercept. If we continue with our graph, it comes up to our y-intercept, and then it comes back down towards that. And notice that it doesn't just touch it, but it goes through it and does a change of shape. So sometimes we call that it crosses the x-axis and changes shape. We can see it in this manner, where we have our x-intercept, we approach it, and then we kind of switch over, swoop over to change its shape. So kind of like a squiggly. If you have a squiggly going through your x-intercept, we say you have a multiplicity of e. So we can see here that the factor x minus 1 that created the x-intercept of 1 has a multiplicity of 3. And that would represent our p of x. And we can kind of see with looking at our end behaviors here that it should be even degreed polynomial, and the leading coefficient should be negative. So if we look at the exponents, we have 3, we have 2, and 1. We can think of that as x times to the 1 power times x squared, that's for the blue one, times x cubed, that's for the green one, and we can get x to the 6, which is even, which our end behavior said that, but we need a negative leading coefficient. So I'm going to put a negative right here. You will be asked to factor polynomials using this method by finding your x-intercepts and determining what's happening at each one so that you know the multiplicity of those factors. Now, this leading coefficient up here does more than just play with the end behaviors. It also helps determine the y-intercept. I'm not going to ask that of you. All I need to know is factors, their multiplicity, and the leading coefficient either being positive or negative. So let's practice that in this last example that we have right here. We'll call it example. We have end behaviors. Notice that our end behaviors are both going up. So that means this must be an even exponent polynomial and that it must have a leading coefficient that is positive. So let's go through from left to right on my graph, and I see that it goes through the x-intercept of -3. That means x plus 3, the factor that created this x-intercept, must have a multiplicity of 1 since it went straight through. It didn't wiggle or change shapes. If we continue with our graph, here I am changing colors into blue. It's going to come down to some value. It's going to try to go back up to x-intercept, but it just misses it. It does go through the y-intercept, and then it keeps going, and then it finds x is equal to 4 as an intercept. Not only does it go through it, but it kind of changes the shape. So we can see that it has a multiplicity of 3. So the factor of x minus 4 that creates this x-intercept has a degree of 3, or an exponent of 3. Notice that if we were taking a look at just the power or the degree of the polynomial, the red one will give me an x to the 1 power, the blue factor will give me x cubed, and together they give me x to the 4th, which does indeed exponent or degreed polynomial, and we need a positive leading coefficient, and that would be my p of x. The only thing that we didn't do is consider what is happening here with these little squigglies, but did not make it all the way to the x-intercept. Maybe there was a quadratic that did not factor or created imaginary zeros that will cause the little squiggles or the little hills and valleys in our graph. But again, like I said, I will be making sure that you do at least this much of our factoring. And notice that you did come up with our positive leading coefficient to explain our end behaviors that we have. This one, like I said, is a little extra just so that you realize that to create those little wiggles in our graph, we needed some other factors that had imaginary zeros. This concludes this video.